Hello and welcome everyone to today's webinar on a software-controlled switched reluctance motor. Before we get started with the webinar itself, I'm Andrea Silvestri and I'll walk you through a few webinar logistics. Today's webinar is based on a report from the Oak Ridge National Laboratory, and you can find the full report as well as a one-page infographic and four-page report summary and additional resources at gsa.gov/GPG. Today's webinar will be recorded, and you'll be able to access the webinar recording and slides also at gsa.gov/GPG under Outbrief Webinars. And we'll also be sending a copy of the recording and slides and the top answers to the Q&A following today's webinar. Today's webinar is one in a series. Our next webinar will be in January, and it will be a GSA internal webinar focused on deployment of GPG technologies. Today's broadcast is set to listen only, and you can use the chat in the right-hand side of the screen, and we suggest that you submit questions, that you don't wait until the end of the Q&A sessions, but you submit questions well in advance. All GPG webinars offer continuing education credit through the American Institute of Architects. And to receive credit, you can complete the post-webinar survey. Now, you won't receive a webinar survey unless you registered for the webinar. So if you don't receive the survey, please reach out to Michael Hobson at michael.hobson@gsa.gov. And speaking of Michael, Michael is the project manager on the software-controlled switch reluctance motor, and he'll be facilitating today's webinar. Michael.
Thank you, Andrea. Hello, everyone, and welcome. Next slide, please. In today's webinar, we'll start with having Kevin Powell, the program director, give us a brief overview of the Center for Emerging Building Technologies and the GSA Proving Ground program. After this overview, we will have Brian Fricke and Mahavir Bhandari from the Department of Energy's Oak Ridge National Laboratory. They will share details and results from our demonstration on software-controlled switched reluctance motors. After Brian and Mahavir's presentation, they will be followed by feedback from Mike Green and Jeremy Zawicki, two individuals from the Land Port of Entry at San Ysidro, California, who were instrumental in assisting us with this demonstration. Jeremy Zawicki is the property manager at the San Ysidro Land Port of Entry, and Mike Green is the one of the lead engineers for the operations and maintenance staff there. Mike Green was assisted us with the installation and also provided very valuable feedback throughout the demonstration and report writing process. At the end of the webinar, we will then instigate the Q&A session, and like Andrea said, please insert any questions into that chat window and we will address them as we can. Finally, with that, let's start this outbrief. Kevin, take it away.
Thank you, Michael. And I feel like as I'm looking at this picture that I need to have one of those Stephen Colbert descriptions of what this guy looks like or something like that. Anyway, I am Kevin Powell. I'm director of the Center for Emerging Building Technologies at GSA. And the key thing to know about our program that we have is that it's the intent is that there's an awful lot of innovation out there, and we're going to talk about one of those innovations. The challenge is that when a company like Software Motor Company that applied to our program and was selected for our program, well, they were selected because we would believe, based on a whole lot of credible data, that they would represent a step change in motor performance, that this is, again, something that really can make an enormous impact. The challenge is, and I think it would be sensible for everybody to be this way, is that we have basically motors are unchanged for 100 years. And, you know, the general way of thinking about things, if it's not broke, why fix it? Well, these motors we know work. They're reliable. They last a long time, and there's a lot of them. So the a reasonable question to ask is this motor really going to deliver in the real world? And that's what our program is set up to answer. We're basically saying for GSA, let's make sound investment decisions in next generation technologies based on their actual performance, the way we install them in our buildings with the people who actually operate equipment, and based on their feedback that it actually delivers. So next slide. I think, again, this slide doesn't need to be any clearer than this. Motors are a huge thing, right? Electricity, more than a third of it in our buildings is used by motors. So if you could improve the efficiency of motors, you would be doing, well, we would be doing great, right? There's an enormous opportunity out there. And the other side of this slide is that more than half of the motors that are making up this large amount of electricity use, just again, broadly speaking, not in GSA buildings per se, but in all commercial buildings, but more than half of them are relatively small, so they're under 5 horsepower. So what we've done in this project is we did this in conjunction, and I do need to say that it's this is a rare case, or perhaps a not so rare case, of the federal government actually working together and collectively and smartly with other federal agencies and with the private sector to look at this motor in a variety of contexts. The context that we took on was actually a larger motor, a 10 horsepower motor in this case, that would have a pumping application. There's other projects that are looking at this in the much smaller size in RTUs, rooftop units, and there's another project that's looking at it in sort of the even smaller motors that are used in commercial refrigeration. So with that, I'm going to actually, next slide. I think this, basically what we want to talk about at this point is to say, hey, we have released this report. We have findings. It's published on our website. You can download that. This is a 4-page findings document. You could also look at the full report, and there's even a 1-page infographic. With that, let me turn this over to the actual presentation of content, and that would be Brian and Mahadir. Take it away.
All right, thank you, Kevin. This is Brian and my colleague Mahadir here. Let's see, I guess we'll go ahead to the next slide. Just a little bit of background before we dig into the meat of the project. Talk a little bit about motors. All electric motors use the interaction of magnetic fields to create rotation. So one type of motor, the AC induction motor, which has been around for over 100 years, relies on electromagnetic induction to create this rotating magnetic field. And so in these motors, there's no magnets used. A recent alternative to induction motors, you may be familiar with permanent magnet AC motors. These actually use rare earth magnets to create the rotating magnetic field. So next slide. So inherently, AC induction motors are fixed speed. The variable frequency drive was introduced in the 80s to allow AC motors to operate at variable speed. And while VFDs allow systems to operate at part load, these devices are an electrical resistance in the system, and thus they reduce the overall system efficiency. And additionally, they're an additional cost to the system. Next slide, please. An alternative motor technology is the switched reluctance motor. This type of motor has been used in the past mainly for zero fault tolerance applications, such as you might see in the nuclear industry. And this is primarily due to the simplicity and robustness of the switched reluctance motor. However, these motors require very complex controls, and they are typically noisy, and so they've not widely been used in building applications. Next slide, please. So the motor that was evaluated in this GSA demonstration is a new software-controlled high rotor pole switched reluctance motor. That's a mouthful to say, so I'll just simply call it a smart motor. So recent advances in electronics and controls have made the switch reluctance motor feasible for a broader range of applications. The smart motor is robust. It doesn't have any rotor windings or magnets, and it can be precisely controlled through the built-in microprocessors and sensors in the motor. Next slide. So here I show a cross-section of an AC induction motor as well as the traditional switched reluctance motor and the new smart motor. So in the AC induction motor, a current and then hence a magnetic field is induced in the rotor when the coils are energized. And so that's shown on the left there. In the middle is the switched reluctance motor. And in this particular type of motor, the magnetic field generated by the energized coils passes through the rotor and forces a pair of rotor poles to line up with the poles of the coil. So if you look in at that figure in the center there, that particular configuration that's shown there, the coil A has been energized, and then the rotor poles 1 and 4 are lining up with that energized coil. So then the next step in the process would be to de-energize coil A and then energize coil B, and then the magnetic flux coming out of the coil B there would force poles 3 and 6 to line up, thereby creating the rotation. So the traditional switched reluctance motor, which is shown in the center there, has more poles on the coil than it does in the rotor, whereas the new smart motor, or the high rotor pole switched reluctance motor, has more poles on the rotor than it does in the coil. Okay, next slide, please. So before we talk about details of the demonstration, I want to make a comment here about motor efficiency. So in this plot, we see the efficiency of NEMA standard and a NEMA premium efficient motor plotted as a function of rated motor power. So a general trend that you can take away from this plot is that lower power motors have lower efficiency compared to the higher power motors. And so those, the standard efficiency and premium efficiency efficiencies are shown with the gray and green lines. And then also on the plot is the efficiency of the new smart motor, which is shown there in orange. And so you can see that the new smart motor is more efficient than either the standard efficiency or premium efficient NEMA motors. And particularly in the case of the lower horsepower motors, you can see a significant increase in the efficiency for the smart motor. Okay, next slide, please. So in this GSA demonstration that Oak Ridge National Laboratory did, a 10 horsepower smart motor provided by the software motor company was evaluated both in a laboratory setting and at a test site. And so the test site M&V was performed at the land port of entry in San Ysidro, California. Next slide, please. Okay, for the laboratory evaluation, the performance of a 10 horsepower smart motor and a 10 horsepower premium efficiency AC induction motor with a VFD were compared using a dynamometer operated under tightly controlled conditions. And then for the site demonstration, the performance of a 10 horsepower smart motor was compared to that of an existing 10 horsepower premium efficiency AC induction motor with a VFD. in a chilled water pumping application at the land port of entry in San Ysidro. Next slide, please. So jumping into the results. So here we see some of the test results from the laboratory evaluation. And what you see here are plots of efficiency as a function of percent full load torque at 3 different motor speeds. And you can see, so the blue line is the NEMA premium efficient motor, and then the red line is the efficiency of the smart motor. And so for all 3 speeds that we've got plotted here, we can see that in all of these cases, the smart motor was more efficient than the premium efficiency AC induction motor. And you can further note that the difference in efficiency becomes more pronounced at lower speeds. So the smart motor is able to maintain its efficiency operating at full speed and lower speeds. So from the laboratory evaluation, we found that on average for the range of speeds that we tested and the loads, the 10 horsepower smart motor was 4.5% more efficient than a premium efficiency AC induction motor and VFD drive. Okay, next slide, please. So on to the evaluation at the land port of entry. For the pumping application there, it was found that the smart motor was more efficient than the premium efficiency motor and drive for a given operating condition. So I should note that for the pumping system that was evaluated there at the land port of entry, it displayed 2 operating modes, what I call a lower pressure differential mode and a higher pressure differential mode, where the pressure difference across the pump and the delivered hydraulic power of the pump showed 2 distinct trends. And then further note, also during this demonstration, a new section of the building was brought online that the chiller served. So in order to fairly compare the incumbent motor and the smart motor, the data was normalized according to these 2 observed operating conditions, the low pressure differential mode and the high pressure differential mode. And for both of these modes of operation, the smart motor was found to be anywhere from 3.7% to 5.3% more efficient than the premium efficiency motor. Next slide, please. In addition to the evaluation that Oak Ridge National Laboratory did in the laboratory and the field site in San Ysidro, this smart motor technology has also been evaluated by the National Renewable Energy Laboratory. In their evaluation, they compared side by side the performance of a smaller 1.5 horsepower smart motor with a baseline 1.5 horsepower induction motor in a condenser fan application in a commercial refrigeration system. Next slide, please. So during the course of their study, ORNL found that compared to the baseline motor with a VFD drive, the new smart motor provided 33% energy savings. And then also, when comparing the smart motor to a fixed speed condenser fan motor, the energy savings was even greater. And in that case, it was on the order of 71%. So again, I want to point out that the ORNL study investigated a smaller horsepower motor than the Oak Ridge study that I just presented here. So, with the smaller horsepower motors, there's more potential for energy savings. So, okay, next slide, please. So other aspects of the GSA demonstration included installation, operation, and maintenance characteristics of the smart motor. So in terms of installation, the smart motor installation was found to be identical to that of all other motors. The smart motors are manufactured with standard frame sizes, so they bolt directly in place of existing motors. And for the chilled water pump application used in the GSA demonstration at San Ysidro, about 12 hours of labor was required to install the motor, and that included laser alignment of the pump and motor shafts. For the condenser fan demonstration that was performed by ORNL, installation time was on the order of 2 to 4 hours. Okay, next slide, please. In terms of maintenance, the bearings of the smart motor are sealed, and so no regular lubrication or maintenance of the bearings are required, and so it would be expected then that maintenance would be reduced for the smart motor. Next slide. The 10 horsepower smart motor that was tested at San Ysidro was a pre-production model, and it was noted that it was significantly louder than the existing premium efficiency induction motor. So 94 dB on A-weighted for the smart motor versus 79 dB A-weighted for the baseline motor. Facility staff at San Ysidro noted that hearing protection would be required when working around the smart motor if it were in enclosed spaces. The smart motor manufacturer recognizes the issue, and they've been working to resolve the noise issue, and they claim with their most recent 20 horsepower prototype operating at a 10 horsepower load that it produces, the new prototype produces a noise level on the order of 81 dB. Oak Ridge has not verified this claim at this time. Next slide, please. The drive for the smart motor does not include an LCD display, as is common for traditional VFD drives. So there, the photo on the right shows a traditional VFD, and you can see the little LCD screen on there. So facility staff at San Ysidro missed being able to directly read operating and performance parameters from the drive itself. However, it should be noted that a computer can be connected directly to the smart motor drive to view and set operating parameters. Next slide, please. So the smart motor does include cloud-based connectivity for remote monitoring and control, and this also allows for fault detection and diagnostics. These capabilities were not tested in the GSA demonstration due to the timeline required to obtain IT security clearance. However, these capabilities were evaluated in the NREL study, and it proved useful when a piece of foam had lodged itself into one of the condenser fans. So you can see a photo there on the right. In that orange circle is a piece of foam lodged there in the fan. So the remote monitoring capabilities of the smart motor was able to alert the team of a fault occurring, and so the fan motor was remotely turned off to prevent motor damage. Next slide, please. The new smart motor is about half the cost of the incumbent premium efficiency AC induction motor and drive. So based on information from the San Ysidro engineering team, a premium efficiency AC induction motor and drive would cost approximately $4,400 versus the smart motor and its drive, which would cost a little over $2,400. I should note that the smart motor is manufactured in China, and a Buy America waiver would need to be purchased, or would need to be in place in order to purchase these motors for GSA applications. Next slide, please. So here we have a table summarizing the economic assessment of the motor. And so given that the smart motor is less expensive than the premium efficiency induction motor and drive, and also given that the smart motor is more efficient, the smart motor provides an immediate payback for end-of-life replacement. applications. However, in a retrofit application, the payback period is pretty long at over 20 years. Next slide, please. So in terms of deploying the smart motor technology, smaller horsepower motors offer the greatest relative savings, as we saw with the ORNL demonstration, where they had savings of on the order of 33 to 70% versus the pumping application at San Ysidro, where it was on the order of 4 or 5%. Savings can more than double when replacing a motor without a VFD with the smart motor. And another opportunity is, since there's a large number of RTUs in commercial office spaces, there's a large opportunity to deploy a smart motor in HVAC fan retrofits. And then finally, the cloud-based connectivity and fault detection capabilities of the smart motor could be beneficial to the GSA. Next slide, please. So in terms of use cases, the best case for deployment of the smart motor would be for end-of-life replacement, again, because the smart motor is cheaper than the incumbent technology and provides a little bit of an energy benefit. In terms of retrofit, replacing constant speed motors with the variable speed smart motor would be an attractive option, as well as replacing motors of less than 5 horsepower or replacing fan motors. Okay, next slide. And so with that, I guess what I'll do now is turn it over to Mike Green and Jeremy Sawicki from the San Ysidro land point of entry to provide their feedback and experiences regarding the use of the smart motor.
Hello, it's Jeremy Sawicki with San Ysidro Port of Entry. Are you hearing me okay?
Yes.
Yes, we hear you, Jeremy. Thanks.
Yeah, so to recover some of these slides, we've already kind of went into the installation of the motor on site here. Just to recap, the installation time was less consuming than a traditional motor, and it takes the 12 hours in order to fully install it. Let's see. So the fan motor installation would be 2 to 4 hours just for the motor itself. Next slide. The maintenance also was already covered. It's in a sealed bearing, so there's no maintenance on the bearing. Next slide. The operations, this was probably the most significant impact to the building and tenants and to the maintenance staff was the noise. We didn't confirm any of these numbers, but it was significantly louder than the existing pump motors that we had. Next slide. Oh, well, I can talk about the VFD screens too. The real-time adjustments for the VFDs was also an issue for adjusting the percentages of the motor was needed for troubleshooting and also for any issues that arise with the pump operation. For recommendations, I guess deploying based on performance, cost savings, and potential long-term savings from a more robust motor design with less maintenance. Test new designs to ensure that the noise issue has been resolved, as we stated, and for integration with the automation system, we'd have to clear the software with GSA IT. Next slide. And any question and answers, we can help you out with any specific questions you have on any of the slides that we covered with installation, operations, and maintenance. We also have the chief engineer here for any technical questions that you might have.
Thank you, Jeremy. And thank you everyone else that participated. So what we've been doing is we've been collecting some of the questions that we have been appearing in the chat window, and we're going to hopefully address some of those. If you have any questions or think of anything in the next 15, 20 minutes, go right ahead and include those. When we deliver the recorded session, we also will deliver some of the top questions and answers that come from this presentation. All right, so I see that lots of people are typing. Appreciate that. We're doing our best to collect all of this information and disseminate it as best as we can. So I'm going to start here talking about one of the first questions. I think it was Keith Welch that asked about the name of the company. The name of the company we work with, and this was a special agreement or a special arrangement through the GSA Proving Ground program. We worked with the Software Motor Corporation who developed this motor. I do believe that there are other companies that are developing similar motors, but we worked with SMC on this. They provided the technology, and we were able to work with them throughout the process. So a question here that I'm going to direct to SMC, or Sam from SMC, I believe, is on the line. I think David is as well. If you guys would unmute yourself. We received a question regarding the high number of poles in the motor and what is the benefit of having a high number of poles. Could you answer that for us?
Sure. Hi, good afternoon, everyone. So a very quick brief answer would be it reduces the arc distance between two poles. That provides more resolution for the rotor across the stator, which reduces the amount of energy required to pull the rotor across one step. So someone pointed out a IEEE paper in the chat. That's a very good paper, and it's written by some of the co-inventors and co-advisors for SMC's SRM technology. So for a more technical dive, I'd refer back to that paper.
Excellent. Thank you, Shams. And we will provide that link for everyone in our next deliverable. Next question here from Alex Bulk, or actually a statement. Alex, thank you for locating that article on the improvement due to greater number of rotor poles. Next question is from Todd Kronline. What analysis was done regarding reliability and maintenance other than for the bearings? And I'll relay that to the Oak Ridge team.
So the evaluation period for this particular project was pretty short, so just on the order of a few months. So we didn't have sufficient time to really address any long-term reliability issues and maintenance associated with that. So definitely, a future study, a long-term reliability study would be beneficial.
Brian, another question. If the motor controller gets damaged from, say, an electrical spike, can that controller be replaced independent of the motor itself? I don't know if you can answer that, Brian, or if that's something that Shams needs to look at.
So the motor controller and the motor itself are two separate units, so they can be replaced individually, yes. Great,
thank you. There was a question out there about connection to the network. We discussed remote access, cloud-based services. Were there any cybersecurity concerns with this motor, and how are they addressed? So I'll start by saying that any technology installed in a federal facility that has remote access requires IT security screening. This is a well-known requirement. We did not utilize the remote access capabilities for this demonstration because of the length of time required to do that screening. We did not pursue cyber clearance, and as Kevin Powell mentioned, we wanted to validate the motor performance first. If we do deploy this as into a future project, we would definitely need to obtain the cyber clearance. But the timeline was not working for this demonstration, and we chose to work around that. So we did not have remote access on this demonstration, but this is something you will definitely need as a requirement to any federal facility. So I have a number of questions here that came up that I'm going to direct to Shams and David Miles on some of the details of the motor. One of the things that we realized with this motor is it doesn't have a display or a screen that could give live updates on how the performance is. Will something like that be incorporated in the future?
Yes, so we're working on a mobile app that would allow commissioning and configuration of the motor controller at the time of install. That's a primary use case we find for that HMI interface, the human-machine interface. And there's a secondary benefit of not having controls there, which is it prevents any unauthorized changing of controller parameters. So by forcing commissioning configuration through either an app or software or the web-based tools that are available when the system is connected to the internet, it creates an audit log, and that's important, right? The statistic we've heard is almost 30 to 50% of VFDs tend to be bypassed in the commercial environments that we're targeting, right? So retail and smaller restaurant-type facilities.
Great, thank you, Shams. While we're at it, a few other questions here. Let's talk a little bit about warranty. Can you give us some details on what a typical warranty would look like for your product? Let's say for a product that is, let's say 5 horsepower. I don't know if there's a difference between the different horsepower that you provide, but let's talk about something around the 5 horsepower. What would a warranty look like?
Yeah, so the motors themselves have a 3-year warranty. The drive, or the motor controller, as we call it, comes with a standard 12-month warranty.
Thank you, David.
And that's across the board for all 4 horsepower motors and drives.
Another question about these motors, how many of these are in real-world applications in industry? That's from Edwin Willite, and I'm thinking that, I think the question is how many of these motors are actually out there?
Let me try and answer that the best way I can. So bear in mind that as it relates to a software motor company, we're a relatively young startup company breaking into a market that is dominated by a number of large players. So we have, in the last year, we've been coming out of going into more of a revenue generating mode. So we have a large number of customers evaluating the technology, and I would say that the numbers in the hundreds right now. The majority of the customers are broadly spread across the commercial spectrum, primarily in the retail and restaurant industries. One of our largest customers is in the agricultural space. So we're driving very large 55 and 72-inch fans with direct drive to those motors. So in that space, there's some other advantages because they've historically been belt-driven systems, which introduce some unreliability in the environment they're used in. So these are big dairy barns, essentially, that get washed down regularly, and we're able to direct drive those. So we have several hundred in that space, and several hundred customers have been evaluating the technology, and a number of those are now going into a full rollout, and we're starting to see orders of several hundred units per customer coming in right now. So it's early days, but the pilots we've been running have been very successful. People are very happy with the technology. They're very happy that they can actually remotely diagnose and remotely monitor the system. And I know that wasn't part of the GSA trial, but that's been a huge value add to some customers who are able to be more reactive about any maintenance that they might need in the system, because we're actually able to tell much more than just the motor's broken. It could be something like a fan belt is broken on a HVAC unit, for instance, and we can tell by the metrics we're able to get from the motor. We're able to kind of provide some of that information.
Thank you, David. Okay. How about one of the other questions are to see if we can have some cut sheets available or provided on the motor in the VFD combo. Can you provide that to us, and can we share that with everyone in the future?
Yeah. What's the best way for us to get those to you and distribute those? I mean, we can certainly provide those. Yes.
Well, they're also available on the SMC website. So if you browse to softwaremotor.com/learning center, you'll find all the data sheets there as well.
Excellent, excellent. We'll make sure we share that with everyone in our next communication on this. I'm going to switch gears a little bit and talk about installation. This is our next question here about installation labor. Mike Green, you might be able to help us with this. What was the need for the 12 hours and the laser alignment? Could you provide a little bit more detail on how the installation went?
So the installation that we did, we utilized the existing ABB drive as a disconnecting means for the motor, because the new SMC motor didn't have a disconnect built into the controls, so that would have been a standalone deal. So we used our ABB drive as a disconnecting means, and then we had to run new conduit from that drive to the controller, and then from the controller back down to the SMC motor. And then after we mounted the motor to the base plate, we used our Vibraline laser alignment tool to get the side-to-side, up and down, and camber within 0.002 to prevent premature bearing and seal failure of the Bell & Gossett motor. The Bell & Gossett pump. And shoot, that's about it, really.
Thanks, Mike.
I'm not sure if that's what they're after, or.
Yeah, I think that answers the question, and if there is more questions, we can definitely address those at another time. Let's keep going here. First, thank you everyone for all your feedback. We've got a lot of questions here. It's great to see how everyone's engaged in this, and there's a lot of interesting inquiries here. So let me continue with a few questions back to SMC. One of the things about RTUs and package AC units is they're typically sold as a system. We don't have a lot of insight on exactly how the NREL demonstration went. We know that there's a report out. We provided the link for everyone to see that report. But could you give us a little information about whether or not it makes sense to replace motors inside one of those systems or one of those RTU systems or components? Or David, I think you understand what I'm saying. You might be on mute.
Sorry, was that directed to myself?
Yeah, to you or Shams, if you could tell us if it makes sense to replace motors inside a already packaged rooftop unit or AC unit.
Yeah. So yeah, that's one of the primary markets we're addressing right now, and we're seeing a huge success with that as it relates to our 1 to 5 horsepower motors, and we're starting to see more 10 horsepower motors going into that space as well right now. So typically what's happening is customers are finding they can get some huge energy savings from replacing, primarily they're replacing fixed speed induction motors with a variable speed solution, and gaining from the benefits of the additional efficiency they get from our motors, as well as the benefits you get from putting in place a variable speed solution. So in a heating and ventilating application, that would be, depending on the heating and ventilating mode you're in, you're running the motor at different speeds in order to be able to reduce your energy consumption. So that's one of our big markets right now, and particularly in the retail, commercial building, and restaurant space, we're seeing a lot of interest in that solution.
Thank you, David. Another question about competitors. Are there other U.S. companies looking to manufacture motors like this that you're aware of?
Well, not that we're aware of, and we have some. One of the things that was talked about was earlier on was the architecture of our motor, where we have we changed the configuration to have a greater number of rotor poles to stator poles. There is a lot of we have a number of patents that protect that model, and there is also a huge investment in the software to drive these motors to be able to maximize the efficiency of the motors, and that's not to be underestimated. You know, there's several tens of man-years of software effort invested in the design of the motor controller that helps us maximize not just the efficiency but the overall performance of the motor in its given application. So we're not aware of anyone right now that is showing any signs of manufacturing this type of motor. They would probably run into some of our patents if they tried to reinvent it. So that's all I'd say on that one.
Okay. There's a note here from someone on the call that mentions that ABB provides these motors. I'm not sure what ABB is, but I don't know if that's something you're aware of.
Well,
yeah, so ABB provides something called a synchronous reluctance motor. It's similar, similar basic technology, but very different in the implementation.
Yeah. And the other thing I'll say is that there is another large motor manufacturer, NIDEC, N-I-D-E-C, a Japanese-based company. They acquired some switch reluctance motors from a UK company several years ago. They do manufacture those motors. They are made for very specific applications, and if you try and buy one, they're very hard to buy unless you've got very large order quantities. It's essentially an OEM kind of type solution. They are not efficient and they're very noisy, is I guess, our experience with those motors.
Okay, thank you, David. Let's continue here with the question about integrating with the building system. How does the motor tie into the BMS? Can it talk through BACnet, for example?
Yes, we have a gateway device called a supervisor, which can communicate a number of BMS protocols, BACnet IP, Modbus RTU, BACnet MSTP is coming up as well. And the motor itself is, some models are capable of talking Modbus RTU directly to BMS. Others are, or future models are going to have BACnet built in as well.
And then to basically set up the motor, do you need a computer to set the motor up, or is that the only option, or is there other ways to set up the motor?
No, at the time we did the study at the San Ysidro LPOE, that wasn't the option. But since then, we're adding a mobile app to allow commissioning. And for most of our customers, the systems are pre-configured before it ships out. So you can either receive a plug-and-play system, or if there's internet connectivity, it allows you to remotely log in, upload a file, which is a much faster process than configuring each parameter on site.
Thank you, Shams. Let's switch. First, if we've still got a few minutes left here. If anyone has any questions, now's the chance to get them on that chat window. We're wrapping up some of the questions that we have currently. So I thank you everyone for your participation. One of the questions came up, and this is something I think Brian you'd be able to answer, or Mahavir. How did you identify typical motors that are in federal buildings that compare to this technology, and then would be recommended for widespread deployment. So I guess the ball door motor, I guess what was it that made you choose that type of motor to utilize as a typical motor use in federal portfolio?
So I think, our, reason for choosing like this pumping application, there at the time were some ongoing and, maybe still going on studies using that motor in fan applications, either like the condenser fan application that I had mentioned about NREL, or I believe there's some ongoing work with using this in RTUs. So, I think there's several studies related to use as fans. So we thought, large buildings typically have chillers, and so that would be another fairly significant application of motors. And they're, on the order of 5 to 10 horsepower motors in those applications. So that's why we decided to go with a 10 horsepower motor in a pumping application.
Another question about the measurement about, so the question is, did you measure shaft currents on both motors?
We did not measure shaft currents on the motors. I do know that at the Land Port of Entry site, they had issues with their existing induction motors and having, premature bearing failure due to arcing across the bearings, however, and, SMC, I think they could jump in and, provide more details about this. But inherent to the design of their motor, there are no currents induced in the rotor, so there would be no arcing across the bearings of the motor.
Yeah. So just to add to that, fundamentally, that as Brian says, that there's no mechanism to generate currents in the shaft of the motor as there is on an induction motor. The induction motor works on the premise that you're actually inducing a current into the rotor, whereas the switch reluctance motors, it's purely an electromagnetic field that makes the rotor rotate. And we've, in the very early days of building our motors, we wanted to make sure of that as well, and we had our motors independently tested to verify that there are no shaft currents, and that testing was done by Aegis, who the company that makes shaft grounding rings. So they had a vested interest in trying to find shaft currents because they wanted to sell us their grounding rings. So the answer is we do not have any shaft currents in our motors.
Okay. What about power factor or harmonics? Did we test that at all? Did we look into that at all?
So in the testing that we did, both in the laboratory and then at the site, we did not measure or, test for harmonics or power factor. Basically what we did was recorded real power going to the motor / drive and then measured output to determine efficiency. So we did not look at power factor or harmonics. But, that is certainly, that's a good question. That would be, some useful information. And I don't know, if SMC could maybe comment on, power factor and harmonics of their particular motor and drive.
Yeah, so the harmonics and power factor for our controllers are essentially the same as what a commercial VFD would show. There's an option to add additional power factor correction and harmonics mitigation devices. And in fact, when our motors are used in IEC applications, so in Europe, there's a kit that can be added with filters and surge arresters to meet the CE, or rather the IEC configuration requirements. In the US, though, in commercial usage, we find that the market's not able to support the extra cost of these items, and so users will go without them.
Well, thank you, Shem. So we've got a few more minutes here, actually a couple minutes. We're not going to be able to get through all of the questions, but I'm going to address one of them from Marcus Zeller. Do these motors operate at typical speeds of 1,800, 3,600, 1,200, 900 RPM?
Yes, they do. And one unique element about switch reluctance motors is they're capable of higher speeds than traditional induction motors or permanent magnet motors. So, for example, we've tested motors up to 10,000 RPM. Obviously, they're not rated at that use, so I can't say you'd want to use them commercially. That would have to go through UL certification. But, you know, the same motor is capable of higher speeds depending on the bearings, etc. Now, the speeds that are listed, 1,800, 36, 12, and 900 RPM, those are all, you know, based on a full configuration for an AC induction motor. We support all of those, and in fact, the same motor model is capable of the full range from 900 to 3,600 RPM, for example, in our 1, 2, 3 horsepower motors. And that's due to the torque production, right? Go ahead.
Yeah, I was going to say that's actually an important factor to consider because unlike induction motors where you would select a 900 RPM or a 1200 or 1800 RPM motor, these motors can deliver the full horsepower range over that entire speed range. So it's another benefit of the motor technology.
All right, we're going to get through a couple more questions here. One of the questions about the laboratory test. Is the test standard from IEEE or IEC available? Is that something that was included in the report?
So the laboratory testing that was performed was done by an outfit called Advanced Energy in Raleigh, North Carolina, with oversight by Oak Ridge National Lab, and they utilized, they tested to a standard, and I apologize, I don't recall right off the top of my head what the number or what that exact standard is, but yeah, it was done according to industry standards for evaluating the performance of electric motors.
We will send that number later.
Yeah.
Another good question here. Let's keep moving. So I understand the controller accepts a number of inputs, such as from multi-stage T-stats, 0 to 10 volt, or BAS, etc. Is that correct?
Yes, that's right.
That's correct.
And shout out to Craig. He's one of our strongest supporters at these webinars.
In addition to that, the motor controller can be programmed to act on those control inputs. So it runs a kind of visual programming language to be able to program how the motor reacts to those different inputs.
All right, the last one I think we're going to have, there's a question about user evaluations and if there's any major issues with the motor per the user. So in all of our GPG demonstrations, we always have an aspect where we interview the users. In this case, it would be the O&M team, and Mike Green, who was part of this presentation today, did give us some feedback on that. In the reporting, that there will be some more details about the installation and about the operation of this technology, as we typically do with all of our demonstrations. So that information is going to be included in our report. Mike Green, I don't know if you want to give any comments about your overview of the operation or installation and operation of this technology other than what you've already told us.
Yeah, absolutely. So the installation went fairly typical. The motor did what it was supposed to do. The only issue was just the noise. Everything else was perfect. It worked just like it was supposed to do. There was no change in flow. Everything performed like it was supposed to.
Thanks, Mike. And that brings us to our final question about the noise issue. And we did talk about this briefly in the presentation regarding the fact that the motor we used was a new model. It was a developmental model. There has been additional testing done related to the noise. We know that noise level that we experience at San Ysidro is lower than it was, or it has reduced in future development of this motor. David Miles, I'll give you an opportunity to talk about that briefly, if you could.
Yeah, so let me preface this just to say that noise is something that has been synonymous with switch reluctance motor technology. It's probably the primary negative factor as it relates to that type of motor. Brian, I think in the full report Brian from Oak Ridge in the full report has done a fairly good job of characterizing why that noise exists, and it's quite a complicated problem to address. But the good news is we have found a solution that mitigates nearly all of that noise, and the testing we are doing right now in our labs, and we're doing this in conjunction with ANSYS in order to be able to create some design modeling tools that would allow us to really make sure that our motors, future motor designs are going to be low noise. So we can model that in software tools and then create new motor designs. But the motors we're testing right now in our labs under most operating conditions are pretty much on a par with other induction motor technologies. Maybe just a little bit noisier, but not in the sense that you would actually object to the noise that's coming from those motors. Certainly from the results that the noise measurement results that Oak Ridge measured on the motors that were installed at San Ysidro, we've significantly reduced the noise on a 20 horsepower motor. So we've elected to prototype 20 horsepower motors and a 2 horsepower motor. The 2 horsepower motors are currently being evaluated in some commercial applications with commercial customers, and they are completely happy that we have mitigated the noise on that particular motor compared to our previous 2 horsepower motors where it's being used in a noise sensitive application. One of the things I will say, where we've been putting the motors in RTUs on rooftops, 95% of the time noise is not an issue there. It's in a kind of benign environment, and it's away from any areas that occupants of the building would experience that noise. Unfortunately, as you go to the larger motors, like the 10 horsepower motors, the noise kind of increases, as per the horsepower motor. So it's very important to address that noise there. So, like I said, we believe we've mitigated that noise now on the large motors and the small motors, and we're in the process of productizing that and creating production models from those prototype designs.
Okay, thanks, David. And there's a question about what the noise sounds like. I would describe it as a very weak whine. Nothing that's going to blow your eardrums away, but it will get down into your nerves if you're exposed to it for a very long time. And that was just the experience at San Ysidro. But of course, SMC has been making improvements in that. I'm going to leave it at one more question, and then we're done. I appreciate everyone staying late for this. A lot of stuff to cover, a lot of interest in this. And the final question, we're going to talk about cost, and I'll leave this open to anyone that can answer it, but the cost of these motors, how does it compare to the cost of comparable permanent magnet motors? Anybody want to take that one?
Shams, I don't know if you have any experience with permanent magnet motors. What I'd say as it relates to a NEMA premium induction motor, our list prices are generally, you mentioned Baldor earlier on. If you looked at the list price of a Baldor motor from their catalog and looked at our prices, our list prices are probably a little bit lower than those motors, but not significantly. So they're in the same order of magnitude as price in general on the 1 to 3 horsepower. I think as the horsepower range grows, as was indicated in the slides earlier, we probably have a bigger advantage there. Shams, do you have any data points on permanent magnet motors as it relates to cost comparisons?
Yeah, that's a good question. Now, it's difficult to make a comparison because quite often it's not an apples-to-apples comparison. The reason being ECMs or permanent magnet motors generally aren't available commercially in sizes larger than 3 or 5 horsepower, right? You might get larger sizes with outer rotor permanent magnet motors, but that's a very different product where the fan, motor, and VFD are built into one package. But general purpose motors such as what we're working on here for the HVAC market aren't really met, you won't really find a good permanent magnet equivalent for them.
Well, thank you, gentlemen, and thank you, everyone, for participating in this outbrief. Andrea, I'll just give the mic to you to close this out.
Great. Thanks, everyone, for being on with us on the webinar and for staying late. As we mentioned at the top of the call, if you complete the survey, you can receive continuing education credit, and please reach out directly to Michael Hobson if you don't receive a copy of the survey. And with that, thank you. Thank you to all the presenters, and thank you to all the participants and your excellent questions.